Hello, my name is Andreas Haeberlen, and I'd like to tell you a bit about our work on differentially private analytics at scale using a system called Orchard. And this is joint work with Ido Roth, Hangchu Zhang, and Benjamin Pierce here at Penn. So to give you a sense of what we are working on, I want to start with a simple example. And this is a feature called predictive typing that's supported by a lot of current phones. And the way it works is, suppose I send an email, an SMS to my student Ido, and ask him whether he's excited for my Google Talk. Ido might start typing a response, yes, it's going to be so in. Okay, and at that point, the phone might have a couple of suggestions, words that he might be about to type. For instance, it might be so interesting or it might be so insane. And it's going to display these words, and then Ido can hit one of those words if that's what he really meant. So how does this work? These models are trained on real user data. So each phone is going to collect some statistics about the words that the user types. And it periodically uploads this information to a central entity, sometimes the phone manufacturer. And this central entity then collects this information and produces a model using all the user data. And then it distributes this model back to the user devices so they can use that model for prediction. And so an obvious challenge with this is privacy, right? So we don't want the aggregator to learn exactly what everybody is typing. Now, this turns out to be an instance of a more general problem called distributed analytics. And so in that scenario, what we have is we have a lot of user devices, maybe millions or even billions of devices that each have some information, maybe about their local user. And then we have a central party, which we call the aggregator, that wants to answer questions about this information in the aggregate. Right? So there's an analyst that supports that supplies queries, and the aggregator wants to answer those queries as best it can. And so what do we expect from such a system? Well, first of all, we want privacy, right? So the aggregator shouldn't be able to tell what the individual users are uploading. We want the results to be precise, right? So there shouldn't be too much imprecision or noise in there. We want the system to scale well, right? Because we might have, like I said, millions or billions of devices in there. And we want security in a sense that maybe the aggregator is dishonest and wants to spy on users or want to learn the user's data, or the users themselves are malicious and maybe upload some bogus information and trying to spoil the query for everybody. So what can we do? And so one idea for getting the privacy guarantees would be to use differential privacy. And at a very high level, what that means is to add a little bit of noise to the answer, right? So to not give a precise answer, but to have a little bit of imprecision in there. And there's a lot of fancy math that has to do with what kind of noise and how much of it, but I'm going to skip that here. At a high level, what it means is really that the aggregator asks how many users typed interesting, and then rather than saying exactly 3,283, we're going to say 3,278, plus minus 10 roughly. And so this approach works well if the data is in a central place, right? So if somebody actually knows the real answer to the query, but this isn't true in the scenario that you're looking at, right? So in our scenario, only the users know the data from their individual device, and nobody knows the really true answer. And what we don't want the aggregator to do is to ask each user to provide their data in the clear, right? So how often did you type interesting? Well, I typed it 4 times, because remember, privacy is a goal, and we want the aggregator to not learn what the individual user's data was. So there is another approach that people use, which is called local differential privacy. And so there, what the users would do is to provide their data with a little bit of noise already added in, right? So the users, rather than saying, I typed it 4 times, they're going to say, I typed it twice, plus minus 10, okay? And this does preserve privacy, but the problem is that the accuracy with this approach is much lower because the overall answer has so much noise, like from every single user in it. And to cite from a SSP paper published by our friends at Google in 2017, they say that the magnitude of this random Gaussian noise can be very large, right? To the point where even a signal from 1 million users can easily be missed. Okay, so there's a lot of noise in there. So, what is really, the problem really boils down to trying to get 3 properties, and we know how to get any 2 of those. Right? So we want high accuracy, we want to scale to lots of users, and we want to do all this with a single aggregator. And the single aggregator and scalability we can get with local differential privacy, but then there's a lot of noise in our answers. If you care about accuracy and having a single aggregator, we can use fancy crypto, and there are lots of ideas like fully homomorphic encryption or multi-party computation, right? But then these things typically don't scale very well, right? So they scale to maybe hundreds or thousands of users, but not easily to millions or billions. And then finally, if we care about accuracy and scalability, right, we can add additional parties, for instance, the Procolo system or in unlinks. But then the question is, how do we actually recruit such parties that are sufficiently trustworthy? And that can be quite tricky in practice. Okay? So how can we get all three? And at last year's SOSP, we published sort of an initial system that can really get all three. And that's we call that system Honeycrisp. And at a high level, the way that Honeycrisp does that is by using additively homomorphic crypto to encrypt the data at the user devices, right? So each user uploads only a ciphertext of their local data. And then the aggregator uses the homomorphism in this crypto system to compute a sum over all the contributions, right? So now they have a ciphertext of the sum, and then we will have elected a committee of user devices, and we distributed shares of the private key across those devices, right? So the aggregator doesn't know the private key and can't decrypt the sum on their own, but what they can do is they can submit the final sum to this committee, and then the committee decrypts the sum and only that sum for the aggregator. So the aggregator learns the final result, and the committee can also add some noise to this result before sending it back. So we achieve differential privacy. So we have a couple of other building blocks in there, right? So we have zero knowledge proofs to make sure that users don't upload bogus data, right? So maybe I can say that I typed the word interesting a billion trillion times. And we have cryptographic protocols to make sure the aggregator actually computed the sum correctly, so that they don't just take one user's data and submit that to the committee for decryption. And we have a technique in there called the sparse vector technique to make sure that we don't exhaust the privacy budget of the differential privacy technique too quickly. Right? And so the system works pretty well, and we're quite happy with it. So you might ask, well, did we solve the problem? And the answer is no. Right? So we solved the problem for one query. And that happens to be a query that has some practical interest, right? So it's the kind of query that, for instance, iOS is using. But there are lots of other queries that you might want to ask. And so this is really just the beginning of a solution. So we have been working on generalizing Honeycrisp to support more queries. And the question is, how can we really do that? And at first glance, that is very tricky, right? Because Honeycrisp's query was simple. It was just a sum, right? Whereas other queries can be quite complicated. So let's have a look at an example, right? So here is a query that we looked at that computes the k-means clustering of a distributed data set. And you can say this is a very complex query, right? So it has complicated transformations in the data. It has control flow. It can have loops. Maybe some people will compute squared distance. And so lots of complicated things in there. And at least to us at first glance, it's not clear at all how you would compute this in this distributed setting. But then we had this realization, which is that a lot of these queries, even though they look very different from the outside and they look very complicated, at the heart of it, it almost always boils down to something like a count or a sum or some kind of sequence or vector or some kind of counter sums. And so what that means is, so in this case, they're right here, right? So these three sums are really at the heart of this algorithm. And so what that means is there is hope, right? So we can try to take these queries and rewrite them in a way that we can take advantage of something like Honeycrisp, right? So Honeycrisp tells us how to do sums and counts, right? And if we can rewrite other queries to just basically consist of sums and counts and some, other things on the side, then we can hopefully execute them in a similar way. Okay? And we're building a system called Orchard that uses this approach. And the way that Orchard works is the analyst writes the query as if the data lived in a central database, right? So with all the users' data in it, which is not true in practice. And then our system takes this query and transforms it into several different pieces, which I'm showing with the different colors here. And then these pieces can be executed by different players in the system, right? So the red piece can be run on each user device. Maybe this is some initial transformations in the local data. The orange piece can be computed as part of the multi-party computation that the committee has to do anyway. And the green piece can be done safely by the aggregator in the clear, right? So many queries do have a piece like some kind of final post-processing that the aggregator can actually do in the clear, right? And so with this, we can execute the entire query in a distributed fashion. How well does this work? well, we are still working on this, but we have some preliminary results, and those look quite promising. So one of the things that we did was we went out and looked at the literature and collected 17 queries that other people had proposed in their papers for differentially private analytics for the centralized setting, right? So without thinking about distributed systems. And we tried to run them in our system, and 14 of them run straight out of the box. And so this is promising, right? So it means that we have something that's fairly general. And the remaining 3 are really not a good fit for our system. Right? For instance, the de-stress is running vertex programs, which are just not don't compute any kind of counts or sums. Right? So that's just not a very good fit for this approach. How expensive is it? And so here it depends a little bit on the kind of query that you're running. But in general, it's not that expensive, right? So for each user, we would typically need something like 1 to 5 megabytes of traffic, and about 1 to 5 minutes of computation on the device, and that can be done in the background, so there's no latency concerns. And this is very scalable, just like Honeycrisp was very scalable, right? So if you have something like 1.3 billion users, you get those numbers, and if you have more, they don't really increase all that much. The overhead per device is almost constant. There's only a very small logarithmic dependency. So where are we going with this? Right, so we're still thinking about a number of other things. One of them is to make things cheaper, right? So how can we reduce the cost, right? So that the user devices have an easier time participating in Orchard. One of them is to deal with more sophisticated adversaries, right? For instance, ones that sort of change their answer between different rounds of the protocol and try to confuse the aggregator. We're trying to make the protocol less interactive, right? This is a concern, for instance, with churn, where user devices might disappear while the protocol is running, and so having fewer rounds of the protocol is better. And we're also trying to support even more queries, right? So things that we can already do quite a few, but it'd be good to have an even bigger chunk of the space here. And most importantly, we're looking for interesting applications, right? So if you happen to have an application that you think could benefit from something like Orchard, please do let us know. We'd love to see whether there's something we can do to help. Right, and so to summarize, the problem that we're working on is distributed analytics at scale. Right, so we have millions or billions of devices, each with some data for the local user, and we have a single untrusted aggregator that we want to answer queries about this data in the aggregate. The goal is to give good privacy guarantees, right, differential privacy, and to also give good accuracy. The approach that we're using is based on this Honeycrisp system that we had at SOSP'19 last year, which works, but it has really only one particular query. And so our insight is that we can use query transformations to take a query that was written for a centralized database and really transform it into one that a system like Honeycrisp with some bells and whistles added can support. And we have an initial prototype that works fairly well and seems to have a fairly reasonable cost. And once again, if you have interesting use cases or interesting applications, please do talk to me. Please contact me. My email address is ahae@cis.upin.edu. Thank you very much.